The number of bacteria in a culture is modeled by the function n of t is equal to 500 Euler at the power of 0.45 t, where t is measured in hours. A. What is the initial population? Population when 0 hours have passed. B. What is the population of bacteria after 2, 3, and 5 hours have passed? C. Graph the model leaving t as a variable. D. Graph a new model from the same equation but with a rate of growth of 20%. E. Based on the two graphs, answer the following. Which question from C or D depicts the model where the population grows faster? Explain why.
I'm sick, doctor.
Oh, you're sick?
Yes.
What do you have? What
I
do you
don't
feel?
know. My stomach, it hurts a lot.
Oh. You know what? Maybe it's a bacteria.
Oh
If it is a bacteria, it can be a population, and maybe it will grow, and okay, we will have many problems if it is.
no! So, in my stomach are bacteria that grow every minute, every hour, every single day?
Yes, maybe not every minute, but yes, every hour, and it is going to grow and grow if you don't have any help or any medicine or something.
And how can I know how many bacteria I have per hour?
Oh, there is a formula, I
I
think.
think there's a formula,
Um,
and I know how to do it.
right?
Yeah.
Let's see. We're going to use the formula for interest compounded continuously. That is n of t equal p Euler at the power r multiplying t. The variables are n is equal to the amount of hours of n of t. T is equal to the number of hours. E o Euler is equal to 2.71. R is the interest rate per hour, and P is the principal. We're gonna change the variables to some terms, like T for 0, 2, 3, or 5, P for 500, E for 2.71, and R for 0.45 and 0.20. So we are going to follow the function of n of t is equal to 500 e at the power of rt. So we're going to use the formula for the initial population of the bacteria in its cell stomach. So we have the formula, but we change the variables t for a 0 and r for a 0.45, and it gives us that it cell has 500 bacteria.
The doctor says I have 500 bacteria in my stomach, but if they are growing per hour, how many do I have in 2 hours, in 3 hours, and 5 hours? If they are growing at 45% every time.
It's simple. The only thing that you have to do is to change the variable t to a number or a term of hours that you want to know the growing of the population of bacteria.
Oh, so we can know how the population of bacteria will grow if we substitute the variable t, which means the time, with the hours that have passed. So, when 2 hours have passed, it means that the equation will be n2 is equal to 500e raised to the power of 0.45 times 2, and the final result will be 1229.80. Oh, I understand now.
But if we change the percent to 20, how many bacteria do I have growing in my stomach in 2 hours and 3 hours and 5 hours?
We have to calculate it because you change the variable t, but now you have to change the variable r to dot 20 to know the percentage of the new growing of bacteria. So the highest is the percentage of the variable r, is the faster the population will grow in your stomach. So the variable r, that is 0.45, is going to cause the faster growth of the bacteria.
Read the problem. Investigate the terms you need of the question. NT is equal to population in that time. T is equal to time. R is equal to relative rate of growth proportion. E, its Euler number, approximately 2.22. Replace the variable T with 2, 3, and 5 with rate of growth for 45% and solve the question. Replace the variable T with 2, 3, and 5 with rate of growth for 20% and solve the question. Graph the question with T as a variable. Observe the differences in graphs. Answer the questions. And conclusion.
In our conclusion, we can say that this document taught us something new, like the concepts of compound interest, exponential growth, and radioactive decay, and their formulas and how to use them to answer problems like on this, when we like to know how the population is growing in a time lapse. Also, the E can be used like a base for this type of equation and not a variable thing. Applications in real life can be, for example, like this problem, to know the growth of a population, to predict its size in a future. Also, it can be used in comparing different changes around a specific period of time, like in studies of mortality rate, studies of diseases or trends. Another application could be in the interest, for example, how they are changing over time, if they are increasing or decreasing. Stewart, Redling, and Watson, 2012, note that the Gateway Arc in Missouri is shaped in the form of a graph of a combination of exponential functions.